We'll continue with the review. Take a look at number 17. When women's wingspans are predicted using heights and r is 0.75, what is the regression equation? So this is something we've done over and over and over. We have x bar, y bar, which is 155, 158. And the SD for x is 8, and the SD for y is 6. We need to find the slope by going right 1 SD, and then we'll go up 1 SD, but we'll shrink it down according to the r value. No, the regression equation comes in two parts, slope and y-intercept. So first we need to find the slope. We will go right 8, and we'll go up 6, but we need to multiply that by 0.75. So 6 times 0.75 is 4.5. So this is 4.5. And now we just do rise over run. The rise is 4.5 and the run is 8. So 4.5 divided by 8, and I get m is 0.56. Does everybody understand that? Now I need to find the y-intercept. That's slope. So we're trying to find mx plus b. We want the equation of this line. So we need to backtrack all the way to the y-axis. That is 155 units. And then I need to go down the equivalent number in y units. But for every x unit, the y unit is 0.56. We're going to do 155 times times 0.5625. And I end up with a drop of 87.2. Does everybody understand why I did that? Okay, let me back up again. To find the slope of the line, we go right 1 SD and up 1 SD, but then we shrink that according to R. So I actually go right 1 SD and up R times 1 SD for the Y values. Okay, and that gave me 4.5. So the slope is up 4.5 and over 8. It's just rise over run. So 4.5 divided by 8 is this number. That's the slope of the line. Now all we have to do is backtrack to the y-axis. Well, I am 155 units from the y-axis. So if I go backwards 155 units, I need to go down 0.56 centimeters for every horizontal centimeter, because that's the slope. So if I go left 155, I have to go down 0.5625 times 155. So when I multiply this number by that number, I get this. And that just represents the distance from here to here. But I started at 158. So the y-intercept is just 158 minus 87.2. Okay, and we'll do this again and again. So, yes. So, what does 67.8 tell us? Oh, 158? I'm sorry. So I need to add 3 to this. So, what does 70.8 tell us? That's the y-intercept. So my equation is y equals 0.5625x plus 70.8. That's fine. Yeah. And you probably did 0.56 instead of 0.5625. That's okay. Yeah, if you're off by a little bit, you're fine. Yes? You could do that. So what Bryn is saying is we have an x and a y and an m. So put m in, put x in, and put y in. That works. And then just solve for b. That's basically what we did. We just did it logically instead of through the formula. So, yeah, if you prefer using that, I mean, that's probably how you learned it 3 or 4 years ago. Okay? All right. Now, the next question says, oh, and let me point this out. This particular equation, is it y on x or x on y? Nope. Y on x. Y on x means we are graphing the y values using the x values. So y on x means we graph y on the x using the x values. Okay? Well, so instead of saying y and x, we will say, so for number 17, that is wingspans on height. Yes. So wingspan on height means that the heights are the x's and wingspans are the y's. Okay? So wingspan on height would be is the equation that we just found. Okay, how would we find the RMS error? We are going to do the square root of 1 minus 0.75 squared times which value? The SD of y, because remember, the RMS error is how far up and down you need to go to capture 68%. So we multiply this by 6, the square root of 1 minus 0.75 squared, and we'll times that by 6. And the RMS error is 3.968. Oh, no. Okay, I'm going to change pages. We're going to do the exact same thing, but this time we're going to do heights on wingspan. So this will be wingspan, and this will be height. And our point of averages is now 158, 155. Yeah. This is question 18. Well, if we were looking at the other graph, then it would be x on y. But we're actually going to draw a new graph. Yeah. It's still y on x, but it's going to be height on wingspan. If it's stated that way, yeah. But like up at the top where we stated heights first, that would be x. Well, it'll say graph wingspan on height or something like that. Wingspan on height would be you are predicting wingspans using wingspan on height. Wingspan would be y. Yeah. Okay, so this one is height on wingspan. Number 18, it says wingspans predicted using height. So that's wingspan on height. In this one, yeah. Okay, so we need to go 1 SD to the right, and we need to do R times 1 SD up, 8. Is the R value going to change? The R value does not change when you switch X and Y. Oh, I wrote 8. I meant 6. 6 and 0.75 times 8. So to find the slope, I need to do 0.75 times 8 divided by 6. So now I got a slope of 1. Okay, so m equals 1. Now this is actually really easy. If I go back 158, how far down do I need to go? The slope is 1. It's up 1 over 1, up 1 over 1, so it's down 1. It's down 1 over 1. So I need to go down 158. The slope is 1. So it's up 1 over 1, up 1 over... Oh, Yeah, up 1 over 1, up 1 over 1, up 1. So for every x, every 1 centimeter in x, I go down 1 centimeter on y. So in order to get back to the y-axis, I have to go 158 centimeters. Yeah, and then I have to go down 158, which is actually going to put me in the negatives. -3. So the equation is y equals 1x minus 3. Okay. And then is this going to have the same RMS error? No. It'll have a different RMS error because SDY. Where are you stuck? Well, if we started up here at 155 and we went down 158, is -3. Okay, so the equation is this, and the RMS error is 1 minus 0.75 squared times 8. So the square root of 1 minus 0.75 squared times 8. So the RMS error in this case is 5.3. Why is it higher than the last one? Because the SD of the wingspan is smaller than the SD of the height. Okay. Now, number 19. What is the predicted wingspan for a woman who is 195 centimeters tall? How many of you did this the hard way and drew the picture? All you have to do for number 19 is plug it into, is it this one or the other one? It's the equation for 17. Yep, so the answer is 0.56 times 195 plus 70.8. So the answer is 180. Now, you could do it the hard way. Yes. Yeah. Uh-huh. Yep. You plugged it in the wrong equation?
No, we did it the hard way.
So you could do this the hard way by saying how many SDs to the right and then go up that many SDs times R and then add that value back to the average, or you just plug it into the regression equation.
So can you do that for number 20?
So number 20, which equation are you going to use? Same one. 0.56 times 137 plus 70.8. So that's easy. Okay. What about the next one? We use the other equation. So we would do 190 minus 3, and the answer is 187. This is number 21. No, you should have the same answers.
So do you get 187?
Well, how close were you, Bryn?
Well, on 17 I got 71.4, and you got, and like they said they got like 7.
Oh yeah, they'll. Yeah, yeah, you might be off by just a little bit. Okay. Okay, 22. Okay, so 22, we're just gonna plug in 149. What did you get for 22? How many? One. Yeah, so it should be 146. Okay, 23. 23 says, what percentage of women have a wingspan over 160? Okay, so we look at the standard normal curve, or the normal curve, and wingspan is 158 with an SD of 6. And we want to know what percentage of women have a wingspan over 160. So that's to the right. we want to find this area here. So, and that's 160. So 160 minus 156 is 4. Divide that by 6, and I get z is equal to 2/3, right? 0.6766 repeating.
Wait. I thought 3.3. So wait, yeah, 0.6.
2/3. It's 2/3.
Why do I have 2?
Okay, so we take 2/3. What do we do with that? We could shade norm. We could shade norm from 0.6. It's not 4. Oh, it's 2. I'm sorry. Sorry. 158. So 2/6 is 0.3 repeating. And you can either shade norm from 0.3 to 5, or you could look up 0.3 on your table and find this area, and then subtract it from 100 and cut it in half, and that will tell you this area. But what do you get when you do shade norm from 0.3? Okay, 37%. Okay. Now, 24 is tough. So pay close attention to 24. Everybody, is everybody okay with 37%? Yeah? Okay. So number 24. Among the women who are 165 centimeters tall, what percentage of them has a wingspan over 160? So the normal population has 37% over 160. If we look at tall women, would we expect the percentage to go up or down? Up. Okay. So I'm going to go back to this graph, right? This is our first graph. And I have the height of 155 here. I want to draw a vertical column around 165. So I only want to look at those people. Okay. So I need the new average. I need this point right here. The easiest way to find that point is to plug 165 into the regression equation. So 0.56 times 165 plus 70, what is it, 71.4, is that what you guys were getting? Okay. And I get the new average of 163.8. So now I create a new normal curve, and the average is 163.8. Does that make sense? Okay, what is the SD of this curve? Because it's no longer 6. It's the RMS error, which we calculated to be, it's on number 17. No, the RMS error, 3.96. So the SD for everybody is 6. But the RMS error for any particular column is 3.96. And we redo all the calculations using the RMS error instead of the standard deviation. So 160, where is 160 in relation to 163? It's on the left. So over here I have 160, and I want this area. So 160 minus 163.8 is negative 3.8. Divide that by 3.9, and I get 0.9. I just found the z-score. So I found the distance from here to here, which is negative 3.8. I divide it by the standard deviation, or the RMS error, and I get 0.93. What does 0.93 mean? It's one RMS error below, so it's actually negative 0.93. Okay? And how do I find the area? Shade norm from negative 0.93 to 5. And one reason why I really like shade norm is if you remember to clear your draw and you forget the negative and you look at the picture, it'll be on the wrong side. Right? If you don't plug in negative and you look at the graph, it will only shade this part, and we want to shade the whole thing. So let's clear the draw, and we'll go. It's not going to be 38. It's got to be larger. Right, so it's got to be larger than 37, and it's over 50%. So 0.82. Did I mess something up?
Yeah, I did not do shaded in the other. Like I got those numbers, but I did not. My new average was 158. So was mine. The 163.8.
Oh, what did I do wrong?
I put 6.
So negative or 0.56 times 165 plus. Yeah, I think we must have messed it up when we did it before. Because using the regression equation.
Don't you do 160 minus 3.9?
Oh, did I type in the wrong number? That we must have typed in the wrong number when we did it before. Because it wouldn't be 160, it would be 165. Okay, so the answer should be 82%. So sorry, if I messed that up last time, I apologize.
Yeah, it made more sense last time.
Okay. Okay, so number 25. What percentage of women have a wingspan from 160 to 170? So I draw a normal curve. I have 158 here. And I want to know what is the area between 160 and 170. So I need two z-scores here. The first z-score, my SD, remember, is 6. So my first z-score is going to be... Oh, wait, I put the 160 on the wrong side. Sorry. Here we go. 160 and 170. Yeah, don't pay attention. Just listen to what I mean, not what I say. So the first z-score is going to be 2 over 6, and the second z-score is going to be 12 over 6. Everybody understand that? So the first distance is 2 divided by the SD of 6.
It will make it easier if you work it out like 160 minus 158 over 6.
Yeah, so it's 160 minus 158 over 6, and then 170 minus 158 over 6. Yes, we need two z-scores in this case. And we definitely want to use shade norm. You don't want to use the table. The table, you could do it with the table, but it would be really confusing. So we need to shade norm from 0.3 repeating to 2. So clear out your draw. And then shade norm from bunch of 3s, to 2. Okay. So that is going to give me 35%. So this area is 35%. 34.6 is what I got. Yes? Yeah, oh, definitely. So this is the answer for 25. So the answer, shh. Hey, we got a lot to get through, guys. The test is tomorrow. No, we've got to get going, so it's going to be tomorrow. No, tomorrow when you show up, I'm giving you the test. Well, I'll do as much as you'll let me if you'll pay attention. Okay, number 25, the answer is 35%, 34.6. Okay? So now we want to look at the women who are 165 centimeters tall. Well, if we go back here, we've already figured out what the new average is, right? If we plug 165 into the regression equation, we got 163.8. Is that what it was? Well, let me look. It's right here. 163.2. So we are just going to look at these people. And we know that the new average is 163.2. And instead of using the SD, we use the RMS error. Because the SD for any column is the RMS error. The SD for every Y value is just the SD. But the SD for any particular column is the RMS error. So my RMS error is 3.9. And I want to figure out everybody from 160 to 170. I need to calculate two z-scores. 160 minus 163.2 over 3.9. And the other one will be 170 minus 163.2 over 3.9. My first one should be negative, and my second one should be positive. So 160 minus 163.2. We'll divide that by 3.9. And I get the z-score of negative 0.82. And then 170 minus 163.2. And we'll divide that by 3.9. And I get 1.74. Now, would I expect my area to be larger or smaller than the last area I calculated? So I'm looking for this particular set of tall women. So regular women's wingspan, we have 35% in that interval. And if I look at tall women, I would expect to have more women in that interval. So I'm going to shade norm. And we're going to shade norm from negative 0.82 up to, oop, thank you. Yes. And we're going to go all the way to 1.74. And now we end up with 75%. So this area here would be 75%. Okay. As any questions on the definitions? Yeah, the definitions will be either multiple choice or matching. Something like that. Okay? So y on x is a regression line that predicts y values from x values, x on y, a regression line, and you can change that into height and wingspan. You guys are okay with the difference between the RMS error and the standard deviation? Okay. So the next set is basically the same idea. You shouldn't need any help with 27 and 28. Well, okay, let's go over. What does 27 mean? No, what does, interpret 3.5 for me. What does that number tell us? Right, but what is an SD? Okay, that's one way to say it. And what we're looking for is, on average, the points are 3.5 inches away from the average. Right, that is the average distance from the average. But it's not truly the average. It's just slightly higher than the average. It's the RMS average. And then, so 28, what does 25 pounds mean? On average, the points are 25 pounds away from the average of 184 pounds. Okay, so 29. Calculate the regression equation that predicts son's weights using father's heights. Is this y on x or x on y?
Son's weight on father's height.
This would be y on x. Okay? So we need to calculate the regression equation. So I know that my point of averages is 70, 184, and my SDs are 3.5 and 25. So I'm going to go right 25, and I'm going to go up how far?
3.5.
Oh, wait, sorry. We're going to go right 3.5. I wrote that wrong.
25 times 27.
And I'm going to do 0.7 times 25 and divide those, and that will give me the slope. 0.7 times 25 divided by 3.5 is 5. So the slope is 5. Y equals 5x. And now we just need to know what B is.
So you go back.
So I'm going to backtrack 70 inches, and then I need to go down 5 pounds for every inch. So 5 times 70 is 350. So 184 minus 350, and it turns out that I drew my graph wrong. It turns out that my axis is more like this, because we're starting 166 pounds in the hole. Did you like my note at the top?
In a totally fake circle.
I just made these up because it doesn't really matter, right? No. Okay. And then we need to calculate the RMS error. So the square root of 1 minus 0.7 squared times 25. Square root of 1 minus 0.7 squared times 25. And I get 17.8. What does this number tell me? On average, the Y values are 17.8 units away from the regression line. So the SD tells you the average distance from the average. The RMS error tells you the average distance from the regression line, which is why why RMS error is smaller, because the regression line hits more points than the average line does. And I have drawn this picture over and over and over, and it looks like some of you are starting to get it. So if I have a football and I draw my Y bar line, that is the average Ys. On average, those numbers are 25 units away from 184. Right? But does that horizontal line do a good job of hitting the points? No, it does a terrible job. So we have a line that does much better, and we call it the regression line. Okay? And on average, the Y values are 17 units away from the regression line. Why is that number smaller? Because the regression line hits more points than the horizontal line does.
It takes less to get 68.
Right. Okay. Good. I'm glad that it finally clicked. Right. And then when you look at a vertical column, you don't use the standard deviation because you're comparing it to the regression line, not to the average. Oh, good. It finally sunk in. I've been saying that over and over and over and over. All right. Well, good. So number 30. 30 says, what does the RMS error mean? On average, the units are 17.8. The Y values are 17.8 units away from the regression line. So the RMS error is basically a two-dimensional standard deviation because we're comparing to the regression line, not to the average. Right. RMS error and standard deviation are both unitless. Well, that's not true. They do have units. They're in inches, but they're in absolute terms. Right. Yeah. Okay. So, if a father is 72 inches tall, predict the son's weight. How do we do that? 33. Yeah, I skipped 31 and 32. How would you do 33? We're just going to plug 72 inches into here. The best prediction we have is to use the regression line. So 5 times 72 minus 166. So if the dad is 72 inches tall, we would guess that the son is 194 pounds. Is that going to be very accurate? 0.7 is really not too bad. So, maybe within 15 pounds or so, we would expect. No, within 17.8 pounds, right? So, so now that you guys understand RMS error, how far away would we expect 194 pounds to be? Within this much, because this number contains R, right? R is the reason why this number is smaller than 25. What if R was 0? What would the RMS error be? 25. What if R was like 0.99? Nope, because it's 1 minus 0, it would be 0.99 squared. So the larger that R value is, larger R will give you a larger RMS error. But if sorry, I said that backwards, you're right. Larger R values will give you a smaller RMS error because the points are closer to the regression line.
So if the RMS is the same as the SD, does that just mean the points are?
There's no correlation. Yep. If the SD and the RMS error are the same number, there is no correlation. But if the RMS error is very small compared to the SD, then your R value had to be really, really high. Yeah, or when you're just looking at one dimension, like percentiles and that sort of stuff. Yes. Okay. Hey, finally, you're getting it. All right. So 34, 35, you're just plugging in numbers. 30, what are you going to do for 36, 37, and 38? You need to do number 31 and 32. Can we just plug 173 in for y in this equation? No, you can't. Yes. Because, so the reason why that doesn't work, if we have our football, this will go through the middle of every column. Okay? But what we want is the middle of every row if you do x on y. So there's a second regression line that looks like this, which those are right across the SD line from each other. So you can predict y's using x's, but you cannot predict x's using y's unless you calculate the other equation, which is what you will do in 30 and 32, 31 and 32. Okay. What percentage of fathers were taller than 75 inches? So we draw our normal curve, and our average is 70, and we want taller than 75. So we want this area over here. 75 minus 70 divided by 3.5, which is 5 over 3.5. And that's my z-score, 1.43. What do I do with 1.43? Shade norm. So clear the draw, and then shade norm, and I'm going to go from, what do I want to type in? 1.43 to 5. And I end up with 7.6%.
And we're shading from there over.
Right. Which is why I like shade norm, because then the pictures will match. If you make a mistake, it'll be obvious. Okay. What percentage of the fathers were between 60 and 70? How would you do that? You would find two z-scores and then shade norm from the lower z-score to the higher z-score. Okay. What percentage of the sons weighed less than 190 pounds? So let's do 107.6. So for this one, the average is 184, and we want smaller than 190, so that would be this area, right? Okay, so 190 minus 184 is 6, and we divide that by 25, the YSD. 6 divided by 25 gives me a z-score of 0.24. Now I shade norm. What do I plug in?
-5.
I want to go from -5, or actually, right? The default is -1,0,0,0,0, a very, very big negative number, I guess you could say, to 0.24. What will I expect this to be when I hit enter? It's going to be close to 50%. Just bigger or just smaller than 50? Should be just larger than 50. Because we're just to the right of the y-axis a little bit. 59%. Okay, and then one of those hard questions. Among the fathers who were 66 inches tall, what percentage of sons weighed less than 190? So now I'm going to go back to here, and I have my regression equation, and I want to focus in on fathers who are 66 inches tall. So this column here, 66. Okay. The new average will be found using the regression equation. So 5 times 66 minus 166 gives me a new average. Oops. That's not going to work. There we go. 164 pounds. Okay. What is the SD of this column? The RMS error, 17.8. So I have a new regression, or a new normal curve with 164 as the average. And I want to find sons that weighed less than 190. So over here is 190. And my RMS error is 17.8. And I do exactly what I did before, but now we're using the new average and the RMS error instead of the original average and the SD. 190 minus 164 over 17.8. Okay. So I end up with a z-score of 1.46. And now I just do the shade norm, and I don't need, the left bound is already defined, 1.46. And we end up with, we were 59% before, and now we're 93%. Why did that number go up so much? So the regular average, the regular people are 59%, the sons. The weight of the sons below 190 is 37%. So when I looked at this column, why did my percentage go up so much? We were looking at a group of fathers that were short. And short fathers have sons that weigh less. So there are more people below 190. Okay. So you could do the same thing for number 44. And then number 45. For the shorter fathers, their sons' heights were taller on average than well, let me try that again. For the shorter fathers, their sons' heights were taller on average than their fathers, and for the taller fathers, their sons' heights were shorter on average than their dad's heights. What statistical reason is there for this phenomenon? Regression to the mean, and the book called it the regression effect, and either one of those works. So it's either regressing to the mean or the regression effect. Okay, do you want to see 43 and 44 before the bell rings? Yeah. Yeah, unless you want to study it. Well, how about I'll solve it and I'll give you the answer, and then you guys give it a try. So you work on it and I'll work on it. So here are the answers for 43 and 44. I got 28% on 43 and 32.6. Did you guys get 28 on the first one?
Yes, but I didn't get. I got 48. I got 41% on the next one.
Did you get the z-scores of negative 3.2 and negative 0.4?
Negative 0.23 instead of point. I got negative 3.03 and then.
So, so negative 58 divided by 17.8. Is that not what you had? Did you get your new average is 178? Oh, it was.
174.
Oh my goodness. I'm sorry.
So I'm right.
I wrote it down wrong. So 174. So that's a 4. Okay, sorry. So
then it's 120.
negative 54 divided by 17.8. Yep, so negative 3.03, and then 4 divided by 17.8 is negative 0.23, and I need to redo my shade norm. So negative 3.03 and negative 0.23. So that area was wrong. It is 40.7. Okay. There we go.